Hello everyone, welcome to another lecture of Microcontrollers with Lab, which is dedicated to the combinational logic circuit design. Now that we know about the decoders and encoders and how, for example, we can implement a circuit, a combinational logic circuit using decoders and an OR gate, it's time to learn about the multiplexers. The main concept behind the multiplexers is the selecting. So selecting or the selection of data or information is a critical function in digital systems and computers. The circuits which perform selecting, they have a set of information inputs. So between these inputs, the circuit will select or will choose one. There will be a single output, so multiple inputs, a single output, and there will be a set of control lines for making the decision or selection, which input should be transferred to the output side. Logic circuits which perform selecting are called the multiplexers. Multiplexer, which sometimes we use also the abbreviation of MUX for them. We can also do selecting using some other elements such as three-state logic or three-state buffers that we will cover later, or it could be done also using a transmission gates. So let's see how the multiplexers work. A multiplexer selects information from an input line, so there will be multiple inputs, and directs the information to an output line. So basically this will be what we have for the multiplexer or MUX for short. There will be multiple inputs and there will be one output. For a typical multiplexer, we will have n control inputs to determine which input line should be selected. So these will be the control inputs. And usually we have n number of them. So the number of the control lines is equal to n, and as a result we can have up to 2 to the power of n number of input lines. So by providing proper value for the control inputs, we determine which one of the input lines will be selected and it will be transferred to the output line. For the control inputs, we can use s underscore n minus 1 to s underscore 0. They are called the selection inputs. And as I just mentioned, there will be up to 2 to the power of n number of information inputs. And we can call them as I to the power of n minus 1 underscore, I underscore 2 to the power of n minus 1 down to I underscore 0. And there will be one output which is denoted as Y. We can have a multiplexer with a smaller number of the input lines, where we will have m number of the input lines, which will be smaller than 2 to the power of n. But here we will indeed consider the typical multiplexers. The smallest multiplexer that we can have will be a 2 to 1 line multiplexer. Indeed, for this multiplexer, we have two input lines and one output line. The output line is Y, the input lines will be I0, I1. So 2 to the power of n here is equal to 2, which means that n is equal to 1, and as a result we will have a single control input, S0. With S0 we control which input to be transferred to the output, so this is 2 to 1 line. When S is equal to 0, we will transfer, or the multiplexer will transfer input I0 to the output. When S is equal to 1, input I1 will be selected and transferred to the output. Finding the equation for this operation is quite straightforward. We can say that Y will be equal to, when S is equal to 0, we will have I0 at the output, or when S is equal to 1, we will have I1 at the output. So Y will be equal to not S I0 or S I1. And the control input here is simply S, not S0, because we have only a single one. Constructing the circuit for this equation is also straightforward and easy. And you can see how it is obtained here. Here we have S. Over here we have the signal not S. Here we have S. Not S. S will appear here. So at the output of the first AND gate, we will have not Si0. Over here, we will have Si1, and Y will be the OR of those two, not Si0 or Si1. So you can see that it is kind of a simple circuit. But if you look at this from another point of view, you can see that we here have a decoder, a 1 to 2 line decoder, and we have a set of enabling circuits, which are basically AND gates with 2 inputs here. And on the output side, we have the OR gate. So that's what we have for the 2 to 1 line multiplexer. It is composed of a 1 to 2 line decoder, there are only 2 enabling circuits, and we have 2 input OR gate at the output side. In order to obtain a basis for the multiplexer expansion, in order to make it easier to design multiplexers with more number of the inputs, we will combine the enabling circuits and the OR gate. So these two parts will be combined with each other, and we will refer them as the 2 times 2 AND and OR. So 2 here is the number of the AND gates, This 2 here is the number of inputs to the AND gates, and we have the OR at the end. So the 1 to 2 line multiplexer now is composed of 1 to 2 line decoder, and then we have 2 times 2 AND OR circuit. And in general, if you want to construct a 2 to the power of n to 1 line multiplexer, what we would need to have will be a n to 2 to the power of n line decoder, and 2 to the power of n times 2 AND OR. So that's the basic, indeed, approach in order to expand the multiplexers. Here we have an example of 4 to 1 line multiplexer. So we have 4 to 1 line. There are 4 input lines, 1 output line. We would need to have 2 select inputs for this multiplexer, 4 to 1 line multiplexer. For the inputs, we'll have I0, I1, I2, I3, and for the select lines, we'll have S1 and S0, and for the output, we'll have Y. So 2 to the power of n is equal to 4. It means that n is equal to 2. That's something that we already know by determining the number of the select lines. And now in order to construct this multiplexer, we can use one decoder of the size 2 to the power of 2 or 4, which is 4, yeah, indeed. So we will have 2 to 4 line decoder, and we will have 2 to the power of 2 or 4 times 2 AND OR circuit. And here you can see the schematic. We have the decoder with the size of 2 to 4 lines, and we have 4 times, so this is indeed not 3, but the multiplication sign. We have 4 times 2 AND, so ANDs with 2 inputs. We have 4 of them, and then we will have the OR gate, which receives input from all those AND gates. So basically, this is how you can construct a 2 to the power of n to 1 line multiplexer using the decoders and the AND and OR gates. We can also expand the width of the multiplexer. Instead of selecting a single bit, we can select indeed vectors of bits. We can select vectors of bits instead of the single bit. For this, we would need to use multiple copies of 2 to the power of n by 2 AND ORs. in parallel. Okay, so one copy of 2 to the power of n by 2 and or will be used to determine the, let's say, bit number 0, another one for bit number 1, the next one for bit number 2 and 3, and so on and so forth. We will use the same select inputs for all these. In this example, we have 4 by 2 and OR gates. They will receive the same select inputs, all of them, and this will be obtained by using the decoder. So you can see it over here as well. Yeah, from the decoder, in this example again 2 to 4 line decoder is used. The inputs to the decoder are the select inputs, and the output of the decoder, which are these indeed signals here, they are connected to the input of the AND gates. So one input comes from the decoder and other input comes from the data. In the case of width expansion for the multiplexer, we will use a single indeed 2 to the power of n line decoder. The select lines will be used from the output of the decoder. They will be shared between all these copies of 2 to the power of n by 2 and OR circuits, and they will receive the corresponding data inputs, data lines, which should be indeed different than each other. So in this case, we will have multiple bits selected at once using a single selection input. So these will be the select inputs. As I mentioned earlier, there are other selection implementations as well, other ways in order to select among the input data. Here we have the 3-state buffers used in order to obtain the selection functionality. So let's see how it works. We have the select inputs here, S0 and S1. We have 2 select lines, n is equal to 2, so there should be up to 2 to the power of 2 or 4 input lines. And we have 4 of them here. So these are the input lines. You should know how the 3-state buffer works. Let's consider different cases. If S0 is equal to 0 and S1 is also equal to 0, if both of them are equal to 0, we have 0, 0 for S1, S0. Let's see what happens. Here we have 0, we have 1 here, 0, 0, 1 is here, 1 is here, and 0 is here. So this is what we have for the enable input of the 3-state buffers. Yeah? So since we have 1 here, I0 will appear here. We have 0 here, so this will be IZ. 1 is here, I2 will appear here. 0 is here, so this will be high Z. This will be also high Z. And then if we look at S1, it is equal to 0. We will have 0 here, 1 here, 1 is here, 0 is here. What we have here will be high Z, and what we have here will be I0. So Y will be equal to I0. In this case, Y will be equal to I0. You can follow it for the other combinations. For S1 is 0 equal to 0, 1, S1 is 0 equal to 1, 0, and S1 is 0 equal to 1, 1. And you can obtain what you will get as the output for the selection circuit. If you compare the gate input cost in this case, it will be equal to 14, which is smaller than what we had for the multiplexers, indeed constructed using the decoders and the AND/OR combinations. Okay, so now that we know how the multiplexers work, we can use the multiplexers in order to implement a given function. There are 2 main approaches for this. The first approach, the multiplexer approach 1, is like this. We want to implement m number of functions of n variables with sum of min terms expressions and an m wide 2 to the power of n2 one-line multiplexer. So m here is the number of the functions. Eventually it could be equal to 1, and n is the number of the input variables. What we need to do here is to find the truth table for the functions. In the order that they appear in the truth table, we will apply the function input variables, so function input variables, to the multiplexer inputs. Input variables will be applied to the s underscore n minus 1 till s underscore 0 inputs of the multiplexer. The outputs will be labeled, the outputs of the multiplexer will be labeled with the output variables if we have more than one function. And then on the data input of the multiplexer, we will do something which is called as value fix. So we'll value fix the information inputs to the multiplexer using the value from the truth table. And for don't care cases, we can apply either 0 or 1. Let's see how this works. So here we have an example of gray to binary code combinational circuit. We want to design a circuit to convert a 3-bit gray code into a binary code. Here we have the truth table indeed. For the function, we have the input in the form of 3-bit gray code, and we have the output in the form of 3 bits, x, y, z. If you follow the formulation, we will obtain this truth table, which you see on the right side. And if you look at this carefully, you will see that x could be found as c. So x is equal to 1 here, and for them, we can see that c is also equal to 1. So x and c will be equal to each other. We already have x equal to c. There's nothing additional that needs to be done for x. But for y and z, we need to find out how it could be implemented, how they could be implemented using the multiplexer. If we rearrange the truth table that we had in the counting order, we will have the updated truth table as you can see here. So inputs and the outputs. Now we need to focus on y and z. The functions y and z needs to be implemented using a dual, because we have two functions. So the multiplexer, we have two layers, let's say. We have 3 number of the input variables. So 3 input variables means that we will have 2 to the power of 3 or 8 data inputs or data input lines. So the multiplexer should be in the form of 2 to the power of 3 or 8 to 1 line max. But it will be a dual one, so with 2 layers. And then we will connect A, B, and C to the multiplexer select inputs, as we just mentioned in the previous slide. We will place Y and Z on 2 multiplexer outputs, and we will connect their respective truth table values to the inputs. So let's see how we can do this. We have 2 multiplexers here shown. You can think that they are a single multiplexer with 2 layers. The select inputs S2, S1, S0 receive data directly from A, B, and C. A, B, and C are connected to S2, S1, and S0. And then for each variable, for each output variable Y, we should look at the truth table. So we know that when A, B, and C are equal to 0, all of them are equal to 0, Y is equal to 0. When all A, B, and C are equal to 0, the first input, or D0, 0 will be selected, and it will be connected to the output. Therefore, the data here needs to be equal to 0. Then when A, B, and C are equal to 0, 0, 1, the value that we have for Y is equal to 1. Here you can see that the second input to the multiplexer is connected to 1, and so on and so forth. So 1, 0, 0, 1, 1, 0. 1, 0, 0, 1, 1, 0. And similarly for Z. So you can basically take whatever value you have in the truth table and connect the inputs, the data inputs of the multiplexer to them. And in this way, we can implement the two functions Y and Z. There is, however, another approach, which is called multiplexer approach 2. In this case, any m function of n plus 1 variables could be implemented using an m-wide, because we have m number of functions, 2 to the power of n to 1 line multiplexer, and a single inverter. So let's see how this could be done. Yeah, here is the design procedure. We need to find the truth table for the output functions, similar to what we were doing for the first approach. Then, based on the values of the first n variables, here, not all the variables, we separate the truth table rows into pairs. You will see how this could be done when we go through the example. And then for each pair and the output, we define a rudimentary function of the final variable, either 0, 1, x, or not x. And using the first n variables as the index, or as the selecting inputs, we will value fix the information inputs to the multiplexer with the corresponding rudimentary functions that we just mentioned here. And then an inverter will be used in order to generate the rudimentary function not x. So let's see how it could be done here. We have the same example, the gray to binary code. We want to design a circuit to convert the 3-bit gray code into the binary code. We know that x is equal to c, so there's no need to do anything extra. Then we kind of rearrange the truth table. So up to this part is what we already have done. But here we create groups of the rows. We divide the rows into groups. So each group here will have 2 rows, will include 2 rows. And if you look at the output side for y, if we check what we have for y here, for y we have 0 and 1. And in this group, you can see that in terms of the input variables, the value for A is always 0, the value for B is always equal to 0, and the value for C is changing. So for C we have 0, 1, for Y we have 0, 1. And it means that F could be written as C. So F will be equal to C. If you look at the Z, Z will be also equal to C. Then in the next group of the rows, A is always 0, B is always 1, C is equal to 0 and 1, it's changing. And if you look at Y and Z, when C is equal to 0, Y is 1, and similarly Z. And when C is equal to 1, Y is equal to 0. Therefore, F will be equal to not C, and similarly for the Z. In the next group, A is always 1, B is always 0, C is changing between 0 and 1. And if we look at the Y and Z, we can see that Y is equal to C, and Z is equal to not C. And finally, in the last group, we have Y equal to not C, and F is equal to C. If you want to implement this now, if we show the schematic that we have for this, 4 to 1 line multiplexers will be used. Now the size of the multiplexer is smaller than what we had in the previous approach for implementing the same function. A and B will be used as the select inputs. We have S1 and S0. And then for the data inputs, we will refer to what we have here. So for the first input, we will connect for the multiplexer that is dedicated to Y. The first input will be connected to C, the next one not C, third one C, and final one not C. And you can see it here. So C, not C, C, not C. And for Z, we will have it, the inputs connected to C, not C, not C, and C. And you can see them over here. C, not C, not C, and C. So depending on the example, sometimes you may end up connecting the input line to either 0 or maybe 1. Okay, so it will depend on the case. And this will be determined by referring to the truth table. If I assume that here we had another output as W, which was we had 0, 0 here. So for W, let's say, you can see that it's always equal to 0. As a result, it will be equal to 0. If we had 1, 1, we would have 1 here. For 0, 1, we could have 0, 1. So it will be C, and 1, 0 will give us not C. So this is just another example which shows you that the inputs could be connected to 0, 1, C, and not C. Those are the rudimentary functions that you already should know. Okay, so that's how a function could be implemented using the multiplexers with two approaches. In the second approach, you can see that the size of the multiplexer is smaller. It is smaller by one size, and as a result, the cost here will be smaller than what we had for the first approach. All right, so I think that's all for this video. I hope you have learned how the multiplexers are working, the concept of selecting, and how you can expand the multiplexers, how can you implement functions, the combinational logic functions, using the multiplexers with two different approaches. Okay, so thank you for watching and see you in the next video later. Bye for now.